In this video, we're going to look at specifically the critical values. This is question 6 on 9.4. We need to calculate Z observed, and if we go and look at the book, to calculate Z observed, we're going to have to take the sample proportion, p hat, minus p divided by the standard deviation of p hat, which is calculated here. So, reading the problem statement, we have p equals 0.45. H is given as, well, the hypothesis, H1, is given as p is less than 0.45. So we take n times p. In this case, we have 1,540 students. Okay, the purpose of this video is to go over the critical value in 9.4. So if you look in through your book, the critical value is going to be corresponding to some Z values or some alpha values, and the alpha would be the area outside of these Z values. Depending on if your setup is the does not equal sign, then it's a two-tailed test, or if it's simply like less than or greater than, it might just be the one-tailed test where you're only looking at one side of it. Your book goes through an example where it does a one-sided test for a greater than sign, and it looks for this p-value here. The p-value is going to be this area corresponding to the z-value of 1.44. So it's going to be the area to the right of the normal distribution curve. So if you would have the area of to the right with z equaling, in the case of the book, 1.44. So if you go to the Z table and look at 1.44, you get the area as 0.9251. That's the area to the left, but we're specifically looking to the area to the right. So if you take 1 minus 0.9251, you get the 0.0749. So that's your p-value. And then when you want to make a decision on your critical value, that depends on your alpha that's given. If your alpha is less than the p-value, that's what you make a decision on whether you're going to reject it or not. So the critical value approach, you have to be very careful if you're doing a right-tailed or left-tailed or a two-tailed. So if you're doing a two-tailed, you're going to have to take your alpha over 2, but if you're just doing a right-tailed or left-tailed, you'll look at that. Here's another example where it is a two-tailed, and you have to take the alpha over 2, and the critical values here correspond to your normal distribution curve of what would give you this area. So let's look at an example from your homework, number 6. We want to find this critical value. We were given alpha is 10%, and in this case we're only a left tail test, so we're only looking at, here we found the Z observed was minus 7.89, which told us the p-value is pretty much 0. But our critical value for our alpha being 10% is we want to look at the area being 10% here. So we're finding the corresponding Z that would give us an 10% area to the left of whatever this point would be. So we go to the standard normal distribution curve, and we're looking for area of 10%, and we want to find the corresponding Z value, which would be our critical. So that's going to be minus 1.28. Going back to this example, here it would be a minus 1.28, which would make sense because it's going to be on the left-hand side. So it would be minus 1.28. Looking at number 14, this is a little bit different one. Calculate the p-value for the test, and we went and found the z-value. The z-value was given at 1.11. That's going to be the area to the right of that. So if we wanted to look at our critical value, our p-value in this case is going to be 2 times that area, right? So considering that we calculate the z observed, the p-value in this case, since we have a does not equal, it's a right and a left one, we take 2 times that area, which is from the normal distribution of z is 1.11. So 1.11 would be this area, but this area is to the left. So if you take 1 minus 0.8665, that gives you the 0.1335. That is going to be the area to the right. If you multiply that by 2, you get the p-value, which would then be able to talk about the alpha value. So this alpha at 0.04 or at 0.1, it turns out you're going to fail to reject both of them because it falls within that p-value. Another way we can say it is for any a greater than or equal to 0.267, we're going to reject the null hypothesis, and for any a less than 0.267, we are going to fail to reject it. So hopefully that kind of answered your questions on where this critical value comes from. And if you have any other questions, please let me know.